Okay, good evening all. We are on module 4 in this study of electronic components. Before I share my screen, as a quick recap, I said there are basic 5 components one is supposed to study in details if you are going to really develop capacity in electronics. Who remember or who can mention those 5 different components? Who remembers? Nobody remembered or remembers. Ben, we were in the last meeting. Did you attend the last lecture? Is Ben there? Okay, let's continue. For later in the meeting, I'll ask the question again. Let me share my screen. Please confirm you can see my screen.
Yes, I can see you, sir.
Okay. So today we are looking at mathematical modeling that has to do with capacitor applications. My name is Engineer Dr. Ekene Samuel Mbon from Federal University of Technology, Owerri. Okay, so let's go ahead. Today we are looking at basic reactive impedance equation. We will look at capacitor's response to both DC and AC signals. We've talked about this, but not in details. We talked about it during the last lecture. So we look at it, especially the way it has to do with AC signal or signals. Then we look at power dissipation in a pure capacitive circuit. We look at power factor correction using a capacitor, and the representation of a capacitor as a complex number. Then we shall look at tutorials and further readings. It's a combination of practical knowledge and the theoretical knowledge. They have to go together. Now, we're at point 1, mathematical modeling of capacitor applications. The basic equation of a capacitor, that's the basic equation for reactive impedance of a capacitor, is given by Xc equal to 1 over Wc, where Wc is equal to 2 pi f. That's equation 1. So, and F is the frequency of the signal or your source. Now, for DC signal, frequency is 0. It doesn't have frequency. So the equation 1 becomes Xc 1 over 0. And mathematically, it gives us an infinite value of impedance. What it means is an open circuit in practical terms. And so it blocks DC permanently or fundamentally. But as F increases, X decreases because Xc is inversely proportional to F. So what it means is that capacitor will act as a conductor at a very high frequency. The key thing to memorize is that here is you have to see, what is this? Just hold on. Um, uh, this thing is disturbing our. Let me just let me share my screen again. Can you see my screen?
No.
Can you see my screen?
Not yet, sir. It's still
No.
moving.
So can you see my screen now?
Yes, sir. Can see you now.
Can you see my screen now?
Yes, yes.
Yes, I can.
Okay.
Yeah.
I was saying that the key thing to memorize is that at a very high frequency, you have to see capacitor as a resistor. I mean, as normal conductor at a very high frequency, because the resistance will have diminished to almost 0. I don't know why this thing is disturbing us. I want to remove this thing entirely from here. Okay. So see capacitor as a resistor at a very low frequency, and then at a very high frequency, just treat it as a conductor because it's going to pass a break signal. Now, in a DC circuit, a capacitor connected in series with the source acts as an open circuit, blocking the DC signal entirely. We come to this point. This thing is disturbing my lecture. Okay. So Let's see. We'll come to point number 2. The charge stored in a capacitor. The charge stored in the capacitor is given by Q equal to CV. I don't know whether you have tried measuring the voltage across a capacitor before. You measure the voltage across a source, the voltage of a source before you insert the capacitor across the source. Is there anybody here who has tried that?
No, sir.
Okay, if you try it, what you are going to get is that immediately after you connect your capacitor, the voltage of the capacitor, the voltage across the capacitor will always be above the voltage of the source. We call it capacitor action because from equation 2, you will notice that Q is always Q is equal to CV. So that effect is called capacitor action. It will cause the voltage to increase a little. And that's one of the reasons why you are not advised to use exactly the same. The rated voltage of capacitor should be a bit above the rated voltage of your source. Okay. Otherwise, if you have a 12 volts supply, same bridge rectifier that is reading 12 volts, the moment you put a capacitor there, it's likely to get to 17, 18 volts. And then if your capacitor is rated 16 volts by 1000 microfarad or 100 microfarad, you notice that you are subjecting that capacitor to stress because the voltage at that point is already above the rated voltage. Now let's consider an AC situation. Consider a situation where V is a sinusoidal signal now. What it means is that the value of Q will be changing from positive maximum to negative minimum within a single cycle. So we have Vt is equal to V0 sine Wt. This is our basic physics. And then pure CVT will be equal to Vt V. That's if we substitute Vt now, we're going to get this. We're going to get this. I don't know. If we substitute Vt equal to V0, where V0 is the maximum voltage, V0 sine Wt, we're going to have this. So the QDT now, there is a slide that is missing here. CV will be equal to C now, V0 CV times, that is CV0 times sine Wt. Let's continue. The current flowing through the capacitor is the QDT. But the QDT will be C dVt over dt. And then if we use the rule of differentiation of a function as function of a function, we are going to get that CV0, that is differentiation of the v dt, will be VW cos sine Wt, because differentiation of sine give us cos And then when we differentiate WT in terms of, with respect to T, we're going to get W. So that gives us CW V0 cos WT. But W is equal to 2 pi F, and the XC is equal to 1 over 2 pi FC, which is equal to 1 over WC. What that leads us to is that WC is equal to 1 over XC. And then we do our substitution now so that IT will be equal to V0 over XC cos WT. V0 over XC is the maximum current. You can as well call it I0. Now let's consider our result at t equal to 0. What is sine 0? Somebody should answer. What is sine 0? I will be calling names, so we did fundamental range physics now. Abimbola, what is sine 0?
I'm not sure. I'm
You say?
not very sure now, sir. No.
You
I said
say?
I'm not very sure now, sir. Peter, probably I'll go with. I said I
You're
am
not
not
very
very sure
sure.
now,
Who
sir.
knows
Probably I
what
might
sine
need to
0
like.
is? You are no longer familiar with your, what do you call it? Basic mathematics. Okay, sine 0 is equal to 0, and then cos 0 is equal to 1. What it means is that at 0 degree, when t is equal to 0, Vt is equal to 0, and when t is equal to 0, t is at the maximum value. Is at the maximum value. I think some of these things, it's good to know some of these things because I still remember that during our maybe secondary school days, stuff like tan 45, cos 90, sin 90, sin 30, cos 30, sin 60, cos 60. These are the special angles you should know they are distinct. For example, tan 45 is 1. Cos 90 is 0. Sin 90 is 1. Sin 30 is the same thing as cos 60, and they are equal to half, 0.5, because they are complementary. This is basic mathematics in secondary school. Okay, and some of those things are playing out here. What does it mean? Let me see if I can exit this thing. This thing is disturbing us. What does it mean? It simply means that x0, v0 over xc is v0 over xc is at the maximum value at t equal to 0. It means the current attains maximum value first before the voltage in a pure capacitive circuit. So we say that the current leads the voltage, or in another way, you say that the voltage lags the current, and that's by 90 degrees, or pi over 2. Pi over 2. That's pi now is 180 degrees. So it's a normal acronym in engineering. When you say ICE, it means that in a capacitive circuit, current leads voltage. And then in an when you say ELI, it means that in an inductive circuit, voltage is current. Voltage is current in an inductive circuit, but in a capacitive circuit, it is the current that is the voltage. We move on. So this is the MATLAB implementation. You can see that V is equal to 220, F is equal to 50, W is equal to 2 pi F. At C equal to 0.332 farad, Xc can be computed. Then for 2 cycles, 1/50, frequency is number of cycles per second, and the period is equal to 1/f. So if you want to get the period of a signal whose frequency is 50, you do reciprocal of 50, which is 1/50, and you get 0.02. So if you want to get 2 cycles like we see here, we multiply it by 2, and that will be 0.02. And then we can now plot, so Vt becomes V0 sine Wt for a range of 0 at increment of 0.002 up to 0.04. And then It can also be computed based on the previous equation. We now plot T against Vt, and this is what you get. So at the time 0, the value of voltage is 0. We move on. When we get to the data of current, still the same thing. You will notice that at time 0, current is at maximum. When you combine the two graphs, this is the graph of current and voltage on one graph. Is it the yellow one or brown one now? The brown color is voltage, while the blue color is the current. So we can see that at time 0, the current is at the maximum. So we say that the current leads the voltage by 90 degrees. And it brings us to the power dissipation in a capacitive circuit. These things are actually, what we are discussing today are the theoretical background that will enable a student to work with a capacitor. It doesn't just end in getting a capacitor, identifying the positive terminal and the negative terminal, that is if it's an electrolytic capacitor, and then putting it in a circuit. We need to have a clear understanding of what we are doing. I mean, a clear theoretical background on what we are doing. So the average power dissipated by a capacitor in an AC circuit is given by equation 4. Power is equal to IV cos theta. That is the real power, where theta is the phase angle. Now, when the phase angle is 90 degrees for a pure capacitive circuit, power is equal to IV cos 90. Incidentally, cos 90 is equal to 0. That's cos 90 degrees is equal to 0. So average power dissipated by a capacitor is 0. The use of capacitor in power factor correction. Based on this information now, that current leads the voltage by 90 degrees, we can begin to see that real power in RLC circuit is given by, okay, let's say real power in RLC circuit is given by equation 5, which is power is equal to IV cos theta. That is effective current flowing through the circuit and the voltage in the circuit. Phase there, or theta there, is phase angle between the current and the voltage signal. In a purely capacitive circuit, current leads voltage by 90 degrees. While in a purely inductive circuit, current lags the voltage by 90 degrees. So it's a situation of plus 90 minus 90. Just look at figure 3. When capacitor and the inductor, when they are connected in parallel through a resistor, you can see what is happening. So the capacitor can be used for power factor correction where inductive load is powered. The ideal value of power factor should be 1, because if the phase difference between the current and voltage is 0, then cos 0 is 1. As the phase difference begins to increase, the apparent power begins to increase, and then the real power, the system that needs to work, begins to decrease. Apparent power is given by IV sine theta. So once the phase angle begins to increase, sine theta begins to tend to 1, because sine 90 is 1. And what it means that the useful power in the system begins to decrease. So there is always need to do power factor correction where inductive load is required. If the power factor correction of our generator is not towards 1, it means that generator will not be doing useful work even though it's on. So capacitor can be used for power factor correction where inductive load is powered, since 90 degrees minus 90 degrees is equal to 0. It will just they will just cancel themselves out if the capacitor and the inductor are connected in parallel, bringing the phase difference between current and voltage to 0. This is what I mean. This is a capacitor, this is a source, these are electric motors which normally are inductive loads. So this one is before the power factor correction. This is after the power factor correction. So apart from using a capacitor to do filtration, using it to do coupling, using it to do what again? Blocking DC, charging function, coupling. Another major use of a capacitor is that it is used for power factor correction. Very important. We come to representation of a capacitor as a complex number. A capacitor is represented as a complex number through its impedance. If the impedance is ZC, it's an imaginary number and frequency dependent. So we say that ZC is equal to 1 over JWC, where J is an imaginary number. And 1 over J is equivalent to minus J, where J is the imaginary unit, which is equal to square root of minus 1. Okay? W is the angular frequency, 2 pi f, I've said it before, and C is the capacitance. The reference is there. You can actually check some of these things off on YouTube. These days, many things are online. They are online. the stuff you may not get online is hands-on. As per theoretical aspect of any subject matter now, you can get it online, but then after reading it online, you have to have a hands-on experience. Otherwise, it will be a theoretical knowledge that may not benefit anybody. So the impedance formula is ZC is equal to minus JXC. Capacitive reactance, the magnitude of opposition to current is equal to S over X is equal to 1 over WC. The phase shift, the minus J terms, signifies that the current through a capacitor is the voltage by 90 degrees, and that is pi over 2 radians. Okay, the angular frequency W is equal to 2 pi f, where f is the frequency in hertz. So in rectangular form, the ZC can be represented as shown here. This is purely capacitive circuit, and the polar form of the representation is as shown here. Let's look at this example calculation. For a 2 microfarad capacitor at 60 Hz, we are required to calculate W. So when we calculate W, that is 2 pi f, we are going to get approximately 377 radians per second. And then we plug it into the appropriate equation to get that the active impedance is 132.6 ohms. The minus there, minus J there means that it's a complex number, and in such a circuit, current leads or the voltage lags, as the case may be. So that's that. The representation of capacitor in complex form, this is actually the way it can be represented. That circuit there, Z is equal to R minus J XC. Now, we're at the tutorial now. We're at the tutorial. Above is RC. Can somebody read what is on the screen? Let me be sure I've not been talking to myself. Somebody read what is on the screen.
Z1 is equal to 100 minus 50i.
Okay, 100 minus
Percentage above is
50i.
an RC.
So
Okay.
above is an RC circuit. Above is an RC circuit. For F equal to 50 Hz, calculate C and R. Of course, R is equal to 100 ohms. And reactive impedance is 50. So you can substitute an appropriate equation and get your readings. A circuit is represented by Z2, that should be 200 plus 300i. Definitely, this is an inductive a circuit with series inductor is in series with a resistor. So the reactive or the inductive impedance, I mean to say, is 300, while the value of resistor is 200 ohms. So with that, someone can easily draw this circuit. You can check out this website. It will give you a good tutorial on RC integrator. Another major important application of capacitor is in RC integrator. You use this as an integrator. Look at this. If you supply this wave here, square wave here, you are going to get a sine wave. Some of these things are, you see, that's why I said anybody that wants to do well in electronic design, we have to study diode in details. study resistors in details, study transistors in details. Transistors, I mean both BJT and the MOSFET transistors. You have to study capacitors in details and study inductors in details. You can cover these 5 areas. There is hardly any circuit you see you won't be able to interpret. And then you can, once you are done with this area, you can get into operational amplifiers. Once you cover those areas, definitely that person will be good. Not covering them on theory, you have to cover them practically so that when you see a circuit, you'll be able to, even if you can't quantify the signal, you should be able to have a rough idea of what that circuit can do and how the signal will flow in that circuit. So this is an integrator. This is an integrator. This is an integrator. So this is a 2-stage integrator. This one, the first stage will give us a sawtooth. That is basic. This is as basic as DC power, rectifier circuit. This will give you, if you supply this voltage here, it will integrate it to give you a sawtooth. Then when you integrate a sawtooth, you are going to get a sine wave. And that's it. Let's see the simulation here. I hope it's opening. It's launching my Pro Tools design suite. It's taking time to open now. Let me see. Okay. Can you still see my screen?
Yes, sir.
You can still see my screen. So let me increase it a little. So this is a function generator. This is a function generator. This is exactly the circuit you saw. This is an oscilloscope. So we run it. It's on square wave. So let's wait for the signal. This is the input, which is the square wave. This is the first stage, channel B, which is the sawtooth, and this is the sine wave. So what it means is that if somebody can actually sit down and think, that person is very close to designing of what now? Can you guess? This circuit, this principle will lead to designing of which product now? No idea.
An amplifier.
Eh?
I said an amplifier.
Amplifier. Yeah, amplifier. No, not amplifier in this case. Well, I don't know whether you know the way inverter works, but at least you know that inverter takes DC voltage. You are aware. The input to an inverter, is it
Yes,
not
sir.
DC voltage from a battery?
This is
Eh?
yes, sir. This is
Is DC voltage from a battery now? The function of solar panel is to charge the battery controller. So we are having a system that takes DC, a square wave is a DC signal on and off, and then you're having an output that is sinusoidal. What is the output of an inverter? Is it not a sine wave? The output of an inverter is a sine wave. So even though this is just fundamental, but at least somebody can start from here and begin to think about how can this thing be developed further to get an inverter circuit. It's all right. So having said that, I think we have come to the end of today's lecture, which incidentally marks the end of study with respect to the capacitor. We have said a number of things about capacitor. We define what capacitor is. We looked at different kinds of capacitor and types. We discussed them in detail, how to calculate their value, what they do, areas of their applications. And then today we look at the mathematical theoretical background, which is required of every engineer should know. Theoretical background. And from the MATLAB presentation, we're able to see, that these things can be simulated, at least for analytical purposes. And then we'll look at the major application of a capacitor, that is with respect to power factor correction. And we also saw today that capacitor can be used as integrators. And of course, I said during the other class, the capacitor are always employing bandpass filters. Okay? When you hear bandpass filters, low pass filters, all you see there is resistor, capacitor, and inductor. That's it. Especially resistor and the capacitor. So if that is the case, it means that one really has to devote time to study these components in detail. Thank you very much for listening. Is there any question for me before we call it a day?
I don't have any questions.
Okay. Bimbola, do you have any question?
firstly, sir. What are those the five I mean?
You
You
said?
mentioned some five.
Can you hear me, sir? Can you hear me, sir?
I can hear you now.
Okay. I said, sir, you mentioned some five topics that one needs to really understand. Because I want to get those topics again. Diode, transistors, capacitor,
Inductor,
inductor.
resistor,
What's the last one, sir?
resistor, and the operational amplifiers. But don't start
Okay,
with
sir.
operational amplifiers. You get the point?
Okay, sir.
Don't start with operational amplifiers, because when you get to operational amplifiers, you will see that they work with capacitor and the resistor. So if you don't understand the basic function of capacitors and resistors, you will not enjoy it. So you study these components. When don't start studying MOSFET without first of all studying BJT, because BJT came before MOSFET. So study BJT, understand them. BJT, I mean bipolar junction transistors. Study them. Once you understand them, PNP and NPN transistors, when you now get to MOSFET, you will appreciate MOSFET better because you will not be talking about P channel and N channel. They're basically the same thing, only that transistor is a current device, while MOSFET is a voltage device. You get the point?
Okay, sir.
So if you section your time and give time to this, within 6 months, that person should be able to come up in electronic design, because every other thing you see in electronics will be a combination of either one or two of them. Okay. Any other concern? So we call it a day. Thank you for